All right, so this would be lecture 2. Lecture 2, which is about an expression language. So we start our excursion through programming languages with the simplest type of language, kind of language that we can fathom. It will have only expressions, not even variables, right? Just expressions made out of constants. And we want to understand how we can, well, really what expressions are in terms of computation, right? So we want to look at semantics, and with this, we want to introduce semantics of programming languages, and we want to look at how they would be evaluated, and also if they were to be compiled, how would we compile them, right? Because obviously this is what happens in most programming languages. All programming languages have expressions, right? It's common. They're pretty standard. There's not a lot of variations. We will introduce, however, a syntax that might seem a little bit strange, just because we're using OCaml in the back end, and it's a notation that is more convenient for us. So with that being said, okay, this is the plan for today. 5 items. All right, and yeah, I'm hoping to be able to go through all of them. It might look like it's a bit much, but we'll just see. Whatever I'm not going to be able to complete during the lecture, I'm going to make a recording and add a supplementary material every week, and that will help us stay on track. We're starting with syntax rules, and we're introducing the syntax as inductive definitions as we introduced them last time. Now, these inductive definitions are a bit, there's a bit of hand waving here, right? So it's worth mentioning that this is actually a schema of definitions. What you see as an n there is every integer constant in whatever range we choose as the range of integers for our programming language, right? So don't think that would be infinite. Typically it's restricted to whatever the hardware supports. We're going to see later that we can have many types of constants when we start discussing types associated with expressions, but for the time being, let's just say that we have one numeric type, right? And that is a very large number of rules, right? If we have, let's say if we assume that the word is 32 bits, right? That would be 2 to the power of 32 rules, each of them having at the bottom the corresponding number. Then we have two Boolean constants, true and false. Okay? So I'm going to put an n here just to, indicate that this is a schema, right? It's not really one rule, it's a rule schema. And then we're going to have a bunch of operators. So we're going to have two types of operators, unary and binary, right? P1 is the set of unary operators, and P2 is the set of binary operators. And we're going to adopt a somewhat strange syntax that has square brackets. I'm going to do a bit more hand waving here, right? So let's remember expressions in mathematics. We would write in mathematics something like 1 plus 2, right? But what does this mean? Plus is really a function. And we have a specific kind of notation which we call the infix notation, right? And if we weren't using plus in the infix notation, we should write it as plus 1, 2, right? 1, 2, because typically we write functions as f applied to a and b, right? The fact that plus is a special symbol doesn't mean anything, right? Plus applied to something, f applied to something, same kind of thing, right? So instead of round brackets, we're going to use square brackets now, right? Just because we want to. And essentially, right, our expressions are going to be either a unary operator applied to an existing expression. So these two rules read in the following way. If E is already a valid expression, then a unary operator applied to E is a valid expression, right? And for the second rule, if E1 and E2 are valid expressions, then P2 applied to E1 and E2 is a valid expression, right? Now, you are going to say, oh, well, but we like our expressions in infix form, right? We like to write 1 plus 2 rather than plus applied to 1 and 2. Okay, so why don't we define the syntax in its infix form? And throughout this course, we're going to sweep that under the carpet. So we're going to assume that 1 plus 2 and plus 1, 2, written with square brackets, are one and the same thing. We're going to equate an expression with its prefix, with its abstract syntax tree, right? That's precisely what we're going to do. So let me reveal a bit more of the hand waving that is happening here. Okay, so you all probably have seen. Let's take an expression, something like 1 plus 2 times 3, right? And you all have seen this kind of tree before, plus 1 star 2 and 3, right? Which is what we call the abstract syntax tree of that expression. So if you see the expression, you understand very clearly what the abstract syntax tree would be. And if you see the abstract syntax tree, you would know what the expression would be. So can we convert automatically between the two of them? Of course we can, right? Can we do it in the context of general programming languages? Of course we can, right? So generally, if I have a program that looks like this, I'm going to use JavaScript which seems to be quite a popular language. I equals 0 while I less than 100, right? Open bracket I plus plus and closed bracket, right? So there's a semicolon here, which we know in JavaScript that is not compulsory, but let's assume it's there. So our syntax tree would be something like this. I'm going to have semicolon at the top, equal I 0 while, right? And I'm going to have less I 100, right? Plus plus and I here, right? So this would be the syntax tree of that program. All right, and we can expand this as far as we go. While it's very easy to understand this correspondence, doing this mechanically and efficiently at the same time requires sophisticated algorithms. In the typical program compiler construction course, right, which would be a way of implementing programming language. So one way of doing this course would be just going through compilers, looking at compilers alone, right? So if we're looking at this translation from the program text to its abstract syntax tree, while the result is very intuitive, you understand exactly how it works, the algorithms are relatively sophisticated, and I would waste about half the course just covering syntactic analysis. These algorithms would be syntactic analysis algorithms. So we're not going to cover them at all. We're just going to assume this correspondence exists without revealing how it happens. Why is that? For several reasons. First of all, you're very unlikely to write a parser for this level of complexity ever in your career. So this is a problem that is very well solved. You would have parsers for most types of problems, and most languages have configurable parsers, OCaml included, that allow us to embed languages and automatically do the parsing without actually writing any parsing algorithms. So it's very unlikely that you will ever need to know how these algorithms work. And even though the algorithms are very sophisticated, right, the output of those algorithms is very intuitive, it's very easy to understand. So I would rather explain to you the correspondence and sweep the way of performing syntactic analysis under the carpet, right? So we're going to talk a little bit more about this issue in a minute. But what I want you to understand when we look at these rules is that when I write P2 applied to E1, E2, I might as well have written E1, P2, E2, where P2 is the corresponding binary operator, E1 plus E2, E1 star E2, E1 and E2, and so on. Okay? Is this clear? Or is it too much hand waving? If you're interested in syntax analysis, I have, one, you can just find the resources on your own. You're old enough to Google, but I have resources of my own if you think that whatever you find online is not sufficient. So, we're going to use parentheses in order to group expressions together. We will use, right, this correspondence, implicit correspondence between the infix and the prefix notation. So this is typically called the prefix notation. And this is a representation of the abstract syntax tree that you have just seen me drawing. Okay? We're going to consider all operators left associative. We're going to use brackets. But outside of during the lecture, we're not going to see expressions in their infix form very much because we're going to talk about abstract syntax tree more. In the lab, of course, you're going to see that, and you're going to have syntactic analyzers provided, right? Parsers provided for what you need to do. Okay, so examples of expressions, right? These would be valid expressions, and they would have their own prefix form, all right? And let's talk a little bit about the typical phases of a compiler, right? So the compiler proper processes an abstract syntax tree, right? It has, once you have the abstract syntax tree, actually writing a compiler, right, processing that to produce a compiler is not so complicated, right? At least a naive compiler, which is why this course is not going to be, is a level 4 course. But getting to the abstract syntax tree requires typically 2 phases. One that is called lexical analysis or lexing, and another one that is called parsing. Lexing does a very simple thing. It splits the program into atomic units, atoms, right, that have a very clear meaning, right? Initially, the program is a piece of text made up of characters, right? But if you think of the units that appear in a program, like a keyword like while or an identifier, right? I might have, I might call my identifier variable 1, right? That variable 1, which is a sequence of characters, as far as the concepts in the program are concerned, is a unit, right? It's just a name, and it will appear probably many times. So we're going to split the input into these atomic units. While would be a keyword, a right brace, right? Then semicolon would be another unit. Any identifier would be a unit. Any operator would be a unit. And notice that some of the operators are made up of multiple characters, right? Like smaller than or equal to. But that smaller than or equal to, those 2 characters will become a single unit after lexing goes through. So imagine now that the lexing phase has completed, and you have this string of atoms. They are data structures, each of them representing an atom in the program. So the next phase is parsing. We are taking this sequence and turning it into an abstract syntax tree, right? Again, this can be done naively, relatively easily, but would require introducing the concepts of grammar. Have you seen that before in a different course? Does everybody know what a grammar is? Who doesn't? Most of you are nodding. Okay, cool. So would require a grammar, right? And would require an algorithm that recognizes elements of that grammar. But doing it efficiently is generally a much more complex job. There are very good tools for building parsers. It's been a very old topic, right? It's one of the first complicated things that computer scientists had to solve. The first compiler was written in the 50s, and that's when this program, this problem started to be studied. And then main research in the 60s and 70s was on compilers. The compilers was the most important topic in computing. That is pretty much solved, right? Compilers are not so exciting. Compiler technology is not so exciting anymore, right? for programming languages research, the emphasis has moved towards design, right? We want to design languages that serve us better. All right, so how would we define the syntax in OCaml? Going back here, we see that we have essentially 4 groups of rules, all right? So this is one group, and remember, it's a very large number of rules. There's another group, there's another group, there's another group, right? So that will give us 4 clauses in a data structure definition in OCaml. So going back here, right, you see the vertical bars, each of them starts a separate clause. And we're going to say that an EPL expression is either a Boolean constant, and we're going to rely on the hardware type for that kind of data, right, which is bool. It's an int constant of int, and similarly, we're going to rely on the hardware data type available for that kind of data. And then we're going to have a unary primitive application, right, which is a unary operator, and the op ID is a string, right? So we have to say which is the operator and which is the operand, and the operand is another expression. Notice the recursion, right? Or it's a binary primitive application of a binary operator to 2 operands, right? Both of them being expressions. So if you look at this set of rules and at the 4 inductive definitions that we had on the previous slide, they match, right? There's a very clear correspondence between each clause and each set of rules. Is this clear? Cool. All right, so we defined the syntax. We know how to write correct expressions. Actually, right, one thing that we haven't quite discussed is what happens with 1 plus true, which our syntax rules don't prevent from happening, right? So according to the syntax rules we discussed, this would not be illegal, okay? But it's clearly something we cannot evaluate unless we make some strange rules of converting true into some sort of an integer and returning an integer. That happens in some languages, right? The people who created those languages are not formally trained computer scientists, on the other hand, okay? But it is a possibility, right? Not one that we're going to consider, though. All right, so we're introducing the notion of semantics. What do we mean by semantics? Semantics means whenever I have a set of things, typically infinite, right? So that is typically that set of things can be built by a set of finite rules, which is the case for us, right? So we have an infinite set of expressions, but we have a finite set of inductive rules that can build that set, right? And we want to derive from those rules a way of assigning meaning. And when you're thinking of meaning, you're already thinking artificial intelligence. But actually, in math, we do a very simple thing. We take this other set, which is the set of meanings, all right? And I take an expression from here, and I want to assign it a meaning from there, okay? Now, what's the most natural set of meanings for expressions? They're values, right? So I'm going to have numbers and booleans. And I'm going to say, oh, I have this expression here, and give me the value of that expression from the set of booleans and integers. Okay, cool? So this is typically execution. If we were in a more complex programming language, we're not yet, but we're going to be there soon, right? If this kind of evaluation would actually transform into become the execution of the entire programming language, a process that can be non-terminating, can go into infinite loop, right? Because a Turing machine is allowed to go into infinite loop. So if we're talking about Turing complete languages, they have to be allowed to go into infinite loop. So because this is runtime, because this is equivalent to running program, we call that dynamic. So in programming languages, we use these two terms, dynamic and static, right? Dynamic means things that we worry about at compile time, that concern us at runtime during the run of the program, whereas static are things that worry us or concern us at compile time, during the compilation of the program. Obviously, all static things have to be terminating. You don't want your compiler to go into an infinite loop. Once a program has been compiled, since that program is unknown beforehand and is equivalent to a Turing machine, it has to be allowed to go into an infinite loop, right? So at runtime, things are allowed to go into infinite loop. So static and dynamic, right? Whatever we do statically has to be terminating. This is a very serious constraint that will limit our ability to derive information at compile time. We'll talk about that later. So a value is either an integer constant or a Boolean constant, right? And we want to derive these values. We're going to do this by defining a number of relations. Everybody knows what a relation is. Can somebody give me an example of a relation? Smaller than, very good, right? So a relation is a subset of a Cartesian product. Right? So let's say I have a relation which I'm gonna denote by circle plus, okay? And I have two sets A and B. So this circle plus is a subset of a Cartesian product B, right? The result of that is if I have some A in small a in A and small b in B, right, it may be the case that the pair AB belongs to circle plus, right? It may be the case. A has to be small a in capital A, small b in capital B. Is that clear? Whenever that happens, we're going to write that A circle plus B. That's the typical notation, okay? If we take smaller than, strictly smaller, just to make it smaller than, I just said strictly smaller, but I draw smaller than equal. So this will be, let's take it on natural numbers, make things easy. So would be a subset of n times n, right? And what are we going to have inside? Well, for instance, 0, 1 is in smaller than, right? As a result, we say 0 smaller than 1, right? 0, 2 is in smaller than. The only way to specify the smaller than relation is actually to enumerate all the elements in it, okay? And that happens internally in our mind. We have already learned what this relation is, and we just use it. Now, we're going to use a relation between expressions, or a bunch of relations between expressions, right? So if we think of the expressions, the set of expressions, as a big expression E, right? We're going to have these arrow-shaped relations that are going to tell us that an expression turns into another expression, right? And then we're going to define that relation by inductive definitions as well. So inductive definitions are going to be the bread and butter of our way of defining things, right? The most basic way of defining things. The first relation that we define is contraction. And it is represented by this symbol right here, which looks a bit weird, but it's very difficult to find good names. So we're picking this one. It looks like greater than and has an index of EPL. Think of it as just a name, right? It's just a weird name, but it's a name nevertheless. It's not greater than with some I don't know, alteration, but it's just a new name. Treat it as a unit. And we're going to say, we're going to define this, right? So contraction is a one-step evaluation, all right? And it is, in principle, the kind of evaluation that can be performed by hardware. And I'm saying in principle. Here, you have to use your intuition and your knowledge of architecture to find a good intuition for contraction, right? But for instance, 1 + 1 evaluates to 2 is a contraction, right? True and false evaluates to false is a contraction, right? And so on. And again, these are not just rules, there are rule schemas. We have to enumerate all the possible combinations. So I have to take all the integers. So V1 has to become all the integers, and P1 has to become all the unary operators. And then what I have here, right, whenever P1 is, let's say, minus. By the way, minus, we might have noticed, we use it as we denote it by tilde, which is the standard or camel way. We don't use the sign minus. So if I say here tilde 1, right, this would evaluate EPL to -1, right? And I have to enumerate that for all numbers. And then I have to go to all the other unary operators and do the same for all the constants. Then I have to go here and do the same enumeration for V1, V2, and P2. And we have rule schemas, a very large number of them, nevertheless finite, right? Because all the data in the computer is finite. That's the contraction relation, right? It's a very stupid way of defining it, but there's no better way. You see, it's the baseline, it's the most basic operations that a computer can do. The good news is that these are implemented in hardware, so you will never have to write by hand all these things when you're building your compiler. You will have to just know how to convert this into the correct assembly language instruction so you get your evaluation done. Okay? But from a theoretical point of view, I'm not telling you what computer I'm going to execute it on. I'm not telling you what architecture. So the only way to start the language, I have to start it from somewhere, is to tell you 1 + 1 is 2, 1 + 2 is 3, 1 + 3 is 4, right? And give you all the rules for all the possible values and operators. Cool? Okay? Any questions so far? So, that was the contraction relation, right? So it's one relation. Notice that that on both sides of this relation we have valid expressions, right? Just that on the right side we always have constants. We never have complex expressions, right? On the left side we have expressions with at most one operator. Actually with exactly one operator. Okay? So we move on to a more complex relation which is called the one-step evaluation. So now let's see what this does. This performs essentially an operation that you know from mathematics as substitution, right? So if you have an expression like 1 + 2 times 3 + 4, right? So 1 + 2 contracts to 3, and 3 + 4 contracts to 7. So I can say that the next step of this expression, right, one possible way this can go is 3 times 3 + 4. Another way this can go is 1 + 2 times 7, right? So the fact that I have a contraction here, anywhere inside a more complex expression, allows me to substitute that expression by its contraction. Okay? This is obviously mathematically valid, right? And notice the fact that if I continue this, I'm going to get to the same result, which is going to be 3 times 7, right? And yeah, more about this later. So the conjecture here is that it doesn't matter, the order doesn't matter. We can go either way. We can apply contractions in any order. We'll still get to the same result. But that's not so interesting right now. Okay, so let's see how do we define this one-step evaluation. So if this is a valid contraction, as defined on the previous line, right, then we also make this a valid one-step evaluation. Okay, this is an operation called lifting. I'm lifting one relation into another. Okay, and then if E, so we already have defined one type of, we got it kick-started, right? We have one type of one-step evaluation, right? So now, since we have one-step evaluations in our universe, we can make assumptions that let's assume that we have a one-step evaluation already present. Okay, so let's assume that this is already a valid one-step evaluation. Okay, E to E prime. Then if I have this expression P1 applied to E, then I can replace it by P1 applied to E prime. Okay, and notice that this one-step evaluation has the property that as we move from the expression on the left to the expression on the right, what we perceive to be the value didn't change. And why do I say what we perceive to be the value? Well, we know what the value of an expression is from our mathematical training, but in the current context, we haven't defined what the value of an expression is yet, right? We are in the process of defining it. And at the end, our expectation is that whatever the definition is, it will match our intuition from mathematics, right? So using our mathematical intuition, we're seeing that as we go from the left to the right, the expected, the value that we assign by intuition to that expression didn't change, right? Okay? So we're talking with different levels of knowledge here, right? So we are defining these things precisely because we have an intuition from mathematics what computation is. We want to formalize it, right? In the process of formalizing it, we have defined the syntax. And now we want to define the semantics. But the semantics is only useful to us if it matches our intuition, you see, from what we have learned in the past. And we are going to use that intuition to assert the soundness of these steps at each step, right? So if E moves to E prime, evaluates to E prime, then P1 E evaluates to P1 E prime. Similarly, we're going to have a similar rule for binary operators, and actually we have to have two rules because here we have two arguments, a left argument and a right argument, right? So if E1 evaluates to E1 prime, then P2 applied to E1 E2 evaluates to P2 applied to E1 prime E2, right? And we do the same for the right argument. If E2 evaluates to E2 prime, then P2 applied to E1 E2 evaluates to P2 applied to E1 E2 prime. Is this clear? All right. So pretty straightforward. So these will be one-step evaluations. Examples of one-step evaluations. They're pretty straightforward. And remember what I was saying, the order doesn't matter. All right. And for this particular language, it really doesn't matter. Right? I mean, it means that we can prove that we will always get to the same result. This doesn't hold in the general case. All right? And there's a certain property that a language needs to have in order to have this property. But this is a property that we like about languages. So when we design languages, right, with their semantics, we want this property to hold. This is called the diamond property, if anyone has heard of it. It was discovered by Alonzo Church for the lambda calculus, right? So I start with an expression. I may apply some E1, let's say. I may apply some evaluation operations in it and get to an intermediate expression E2. Or I may take a different route and apply some different evaluation operations and get to an expression E3. And what we want the language, the property that we would like to have is that if E4 is an expression, if I can get to this E4 from here, right? If from E2 I can go to E4, And if 4 is the one expression that cannot be further simplified, then it must be the case that E3, that there's a sequence of steps that lead me from E3 to E4 as well. Okay, it's called the diamond property. Obviously, there's a diamond there. It's a property we generally like and want to have of a language. All right, the full evaluation relation, which is the reflexive and transitive closure of the one-step evaluation, right? So you know the notion of closure, right? A relation that is closed, right? The result of any operation is part of the relation as well. So how do we construct the closure? Well, any sequence of evaluations have to be part of the closure. So again here, treat this as a name for the relation. This is a name. The star there is not an operation. It's not an operator. Okay? It is similar to the star for regular expressions, right? You know from regular expression that we say, oh, A is a regular expression, and I say A star. And when I say A star, I mean 0 or more repetitions of that regular expression, right? So it's the same kind of thing, right? Just that you might think that the star is an operator applied to the relation. So sometimes that intuition holds, sometimes it doesn't, right? So I don't want you to be focused on that right now. Take that as a name, right? Take the arrow star as a name for a new expression, which is the full evaluation relation. For a new relation, which is the full evaluation relation, right? So we're defining that via a set of inductive rules. And the first rule always is the lifting rule, because we're basing this relation on a previous one. So we're saying that anything that evaluates in one step is also something that is part of the full evaluation relation. So one step of evaluation is it has to be part of the transitive closure, right? So it's part of the new relation as well. Okay? Then it has to be reflexive and transitive. Reflexive means that any one expression is in relation with itself. So E is in relation with itself. So this is the second rule. And then if E1 is in relation with E2 and E2 is in relation with E3, then it must be the case that E1 is in relation with E3. This is transitivity. Cool? So now we're interested, starting from an expression, in all the expressions that are in this relation with the original expression, especially the one that is no longer reducible. All right? And our intuition tells us that there should be such an expression that is no longer reducible, right? The proof is actually quite simple, because at the base of this, all these relations we have defined, there is the contraction relation. The contraction relation always removes an operator. So moving from the left side to the right side, we always have one less operator. Since we have a finite number of operators in any expression, by applying this full evaluation relation, right, at each step we're going to lose one operator till we're going to lose them all, at which point there's no more rules to apply. So every complex expression must evaluate to something that is further irreducible. Okay? So that also gives us an idea on how to implement this. Right? The evaluation of an expression is, if the expression is reducible, then apply an evaluation step, right, and further evaluate. Otherwise, return the current expression because it's irreducible. Cool? So this is an expression evaluation. Of course, we have to define the reducible predicate, and we have to evaluate to define the one step. What do we mean by one step? Okay, so that will be part of the lab. Any questions so far? Yes?
Go back to the previous. On the top right one, why do you need that? It seems that.
The top right one, this one?
Yeah.
Oh, because of this, I'm returning E, right? That's what allows me to, the evaluation of E is E when E is irreducible, right?
Because, but when it's not reducible, then it just retain.
But that will complicate our relation, because, so what you want here is that E is in relation with E only when E is irreducible, right? But I don't want to bother with defining what irreducible is inside this relation. So it definitely doesn't hurt.
What I mean to say is from the top left one, if E1, can E1 and E2 be the same for the
No, because if you look here, they're never the same.
Okay, if they're the same, then means it's irreducible.
But so the one-step evaluation, you never have one, on the left and the right. You never have the same expression.
Okay.
Because the one-step evaluation means at least one contraction, and one contraction means one less operator. So they can never be the same. All right? Yes?
On the previous slide, what is the BRT?
So we're naming the rules, right? R is reflexivity, T is transitivity. I have no idea what B is, since they're not my slides. So I would have called that lifting, because you're taking one relation and moving it into the left. But probably it stands for basic, or base. It's the basic relation. It's the basic rule. So we're naming the rules because later we might want to refer to them. It's standard practice in defining inductive rules, right? Notice that we've named, actually, I think we've named a lot of the rules. Yeah, so we've named these rules as well. So you want to see contraction, that's a name of a rule, OPAR 1, OPAR 2, OPAR 3. They're the name of the rules. So in the notes, we might be able to refer to them in different parts of the text. Yes?
Can you make sense for that lifting, converting them to?
No, so lifting is you're defining two notions, right? But the new notion is, you're defining a new notion based on an old one, right? So typically what you do is the most basic definition for your new concept, right, is the old concept. So that's essentially called lifting. You're lifting the old concept into the new concept, right? So we've done that twice. So notice here that right. So whatever is in the old relation is also into the new relation. But if we go here, we've done exactly the same here. Whatever is in the old relation is in the new relation as well. Right? So we're defining a hierarchy of relations where each new relation is starts as a lifting of the old one. Cool?
For that reflexive, the final irreducible thing,
Yes?
defines that reflexive relation, right? Like if I'm not able to reduce that further expression, that
So,
basically defines the.
if you're not able to reduce, the evaluation of the irreducible is itself. Right? Cool. More questions?
Is EPL, EXPR is a type in vocabulary? Here the notation.
Yes, we have just defined it. Let me go back. Here, right? It's this type. All right. Static semantics. So again, notice that we haven't said what happens with 1 plus true. Right? So we're assuming that the hardware will bomb when we try to evaluate 1 plus true. Right? Because we haven't provided any rules specifically for that. Yes?
I thought we already said that there's some mapping that you're just like we had the less than example that you had
Uh-huh.
0 less than, or we had those as a subset of the results.
But plus is not really a relation. Plus is an operation.
Right, but isn't
It is also
it also a relation? So how do we define
So 1 plus 2 would contract to 3,
that?
and you would expect there that if you say 1 plus true, you would say that 1 plus true simply doesn't contract to anything, right? Right. Okay, so that would be right. So what would the so that would be the irreducible thing. Okay, cool. Okay, that's a neat understanding. So 1 plus true is just irreducible, and it's its own evaluation. All right, which is sort of interesting because 1 plus true is something we don't really have a meaning for, and but it's a sound interpretation of the rules. So thank you for that. Everybody understands what we're talking about? Right. So we haven't said what happens to 1 plus true, but what's your name, by the way? Stephen, all right? So Stephen was pointing out that 1 plus true, actually, according to the contraction rules, is irreducible. Okay, because if we go here, too far. If we go here, right? So we would expect 1 plus true, right, to match one of these rules, but it doesn't, right? So 1 plus true doesn't contract to anything. So it is therefore irreducible.
The reason it doesn't because we haven't defined it.
But what would you define it with?
No, I just don't understand why it doesn't match.
How would it match? What would you put here? So this is a rule schema, right? It's a big set of rules, right? And I would enumerate all the valid arguments v1, v2, and all the operators. But since 1 and true are not valid arguments to plus, the 1 plus true will not appear in that rule, right? 1 plus true will never appear anywhere on the rule in the rule schemas.
1 and 2 is not a valid argument to plus.
Why not again?
Why the 1 or 2 is not a valid argument to plus?
1 or true. So 1 plus true.
Or 1 plus 2. Sorry.
Okay, I'll try to speak more clearly. So 1 plus true are not valid. 1 and true are not valid arguments. True are not valid arguments to plus. Therefore, this they would not match any of the rules, right? Therefore, this expression is irreducible. So when we try to evaluate it, it will become its own value. Okay, so good point, Stephen. Thank you for that. All right, static semantics.
Excuse me,
Yes?
where are you capturing that B1 and B2? Can you go back to that?
Okay. Here or here?
Yeah. So where are you capturing B1 and B2 should be with an integer or?
I'm not. So I'm saying that these are schemas of operations that are defined in the hardware, right? So what I want here is to write an expression that the hardware can evaluate, and what I would write as the V is the result of that operation, right? So we're assuming an intelligent hardware that differentiates between true and any non-zero value, which actually does not exist, but one can dream, right? but we're assuming that. So think of this as the set of all possible rules, of all possible operations done by hardware. Right, so 1 plus 1 will be there. The value of 1 plus 1 is 2. So on the right side we have 2. 1 plus 3, 1 plus 4, 2 plus 1, 2 plus 2, 2 plus 3. All the pairs, right? And all the operators. 1 star 1, and so on. And 1 and true will not be there. Because our assumption is that the hardware would know to differentiate between numbers and Boolean values and simply not reject that rule, not evaluate it, not have an evaluation rule for that. Okay, you're shaking your head. Why? No? It's okay? That's your sign of approval? And you
by saying you'll be handled in hardware, that means we will not care about 1 plus 2 or this kind of.
well, no, obviously you have to care, right? So when we're talking about static semantics, which is the next topic, right? We're going to clearly say that there's no static semantics for that kind of expression, right? So we're not going to even bother to try to evaluate. So that would be that would be our safeguard. So we're going to do a static check first, and only then allow the expression to evaluate. So we don't even need to think what happens when 1 plus true gets to the hardware. Okay? So, true plus 1 does make sense, right? We like a way to figure that it doesn't make sense before we try to evaluate, right? And for that we invent types. So what are types? A very short history. You've probably looked at various languages that have types and figured out that, int and bool, they're just two sets. They're like sets of values, right? Things are a bit more complicated than that. It also is important to have types in modern programming languages because that gives you the encoding, right? Looking at the bits inside the contents of that variable, you know how to interpret them, right? If it's an int, the bits are interpreted differently than if it is a double, right? It's all bits. So what you have is 64 bits for a long and 64 bits for a double, right? But if you take if you're in C, how many of you are familiar with C? I think C is less and less popular these days. But one thing that you can do in C is you take an int. So let's say I is an int, and I can say double star ampersand ampersand I, which is our integer, right? And this, guess what, is a pointer to double, which when I dereference, I would get the bits of I interpreted as a double. All right? And I can do the reverse for it can be done in Java as well, I think. No? You don't agree? You understand the notion of bits? 64 bits are 64 bits. If I look at them as an integer, I get one integer value. If I look at them as a double, I get a completely different thing, right? So types are important for that reason as well. They were invented actually by a very long time ago by a mathematician called Bertrand Russell, turn of the 20th century. He was trying to get rid of a paradoxon in naive set theory. Do you know what the paradox was? Russell's paradox? Anybody has heard of it? Yeah, well, it's related to that. It's a bit more technical than that, right? So, do you know sets that contain themselves? Think of that. Sets that contain themselves.
The empty set.
The empty set? How does it contain itself? The empty set doesn't contain anything, so it can't contain itself.
Yeah, that's a paradox.
That's not a paradox.
Like all sets, like if you define sets as containing themselves,
Right.
then what?
Can you give me an example of a set that contains itself?
Not contain itself, a subset.
if every set is a subset of itself.
But every set is a subset of itself.
The empty set is that
Set that contains itself.
A set of
The
all
set.
sets containing itself.
Louder, please.
A set of all sets containing.
The set of all sets contains itself, right? It is a set, so it has to contain itself. The set of all infinite sets contains itself. It is an infinite set, contains itself. The set of all sets describable in English in less than 1,000 characters. I just said less than 1,000 characters. That set contains itself, right? So there's an infinity of sets that actually contain itself, as long as we are allowed the freedom of English to describe them, right? So since we have sets that contain themselves, we'll split the universe into two types of sets: sets that contain themselves and sets that don't contain themselves, right? And any set will be either containing itself or not containing itself. These two are disjoint. So if I denote by A the set of all sets containing themselves, and by B the set of all sets not containing themselves. Since B is an element of the universe, where is B? In A or in B? Well, let's assume that B is in A. By the definition, B is in B. And because B and A are disjoint, that's the paradox. Very simple, right?
Why is B a part of A?
Well, I'm assuming. So if I assume that B is part of A, I'm getting that B is not part of A. Right? If I'm assuming that B is not part of A, I'm going to get that B is part of A. So I cannot put B in either A or in B. B is nowhere. It's not in A, it's not in B. Right? So sets containing themselves actually are not a good thing. They should be banned, right? Russell tried to use types to do that. He wasn't really successful, all right? He was trying to remove contradiction from logic completely. The answer was given much later in a very strange way. Do you know the answer to that? Removing contradiction from logic, yes.
That was Gödel's
Gödel's incompleteness theorem, very good.
Yeah, that any formal system basically has to have self-references, and that
Yeah.
and basically you can't create a formal system without these paradoxes.
No, so you see, what you want from a formal system is completeness and consistency, right? You want it to be consistent in the sense that everything you prove should be true in real world, and you want that everything you query, any question you have, you should find the answer that is either true or false. Of course, any question of the type true or false, right? That, a yes or no question, you should be able to prove that it's either true or false. So he showed that these two things are not simultaneously possible, right? And you need to give one up. People were trying to get completeness and were getting inconsistency, which are the paradoxes. So modern systems have figured out that they prefer to have consistency. Consistency is better, and we can allow incompleteness. There are things in our theories that we cannot prove, right? But anything we prove either true or false should be true or false in real life. So that was Gödel's paradox. Perfect formal systems are not possible, and the practical world has decided that they should prioritize consistency over completeness. Anyway, you have a course in logic. When I was here 5 years ago, I used to teach that. So if you want to know more, I'm sure there are opportunities to do that. Okay, types. So we're going to build a very simple theory of types, And that's going to get more complicated as we introduce new elements and we make the language more complex. So you know what it is, right? I don't have to explain the examples here, right? We want obviously to whenever we have true plus 1, if we want to assign a type t to it, we must infer that that type doesn't exist, right? Obviously, we always want to infer the correct type. So if we want to assign bool to the type of bool to an integer expression, that should not hold in our system. How do we do this? With inductive rules as well. So we're going to define all the primitive types. So true and false are booleans. All n. So again, this is a rule schema, right? All the numbers in our system, we have to have a rule for each of them and say that they are integers. All right? And then we have inference rules. Inference rules would have a premise, right? There's something above the bar. So if e is of type int, negation of e is of type int. If e negations, right? So the minus e, negative of e is an int. If e is a boolean, negation of e is a boolean. If e is of type t1 and e1 is of type t1, e2 is of type t2, then p applied to e1 and e2 is of type the corresponding type t. So that type t depends on p. For instance, again, this is a rule schema. If e1 is int and e2 is int, and if p is plus, then t should be int as well, right? If e1 is int and e2 is int, and p is less than, then t should be boolean, right? So if we take all the operators, because these rules are dependent on the operators, if we take all the operators, we would know what t1, t2, and t should be, right? And this should be the basic inference rule for all the ways of constructing an expression. So if you look at these rules here, they're in direct correspondence with the syntax rules that we first define in the syntax of the language, right? The first rules that we saw were syntactic rules for the language. For each rule that we have there, there's one rule that we have here. Okay? Cool. Okay? And this is static semantics. This is how we define static semantics. This is obviously finite, right? But so was the evaluation. The evaluation was obviously finite. However, we'll see when we move on to more complex languages that the type inference will always be finite, right? It's static. It's a static thing. This table contains the combinations of types for the last rule on the previous slide. Okay? And it is exactly what you expect. So this is very straightforward. Okay? So we're saying that an expression is well typed if there is a type t such that e has type t. And we want from this point on to submit to evaluation, to subject to computation of dynamic semantics, only those expressions that pass the static semantics. In our case, those expressions that are well typed. Okay? So, let's go through a very quick proof that 2 times 3 greater than 7 has type bool. Right? So we start from first principles, right? So what are we going to do? How is this a proof? Well, each level is an instance of a rule, right? So this is a rule. This is a rule. Then this is a rule. Okay, this is another rule, and then this is another rule. Okay? So we stack rules in this way, and we get some sort of a tree, and that's a proof that the type of an expression is what it is. Okay? We can apply the same mechanism for evaluations, by the way. We can have a similar tree, right? Because we define evaluation in terms of rules. Just that, that's going to be more complicated because we have 3 relations. Okay, So you're going to get a much hairier tree. Is this clear? Obviously, we can compute this automatically. We don't have to do it manually. We can write a piece of code that constructs this proof internally and derives the type of an expression. Cool? So we have an implementation idea. We can work bottom up, right? And trees are always tricky, right? Because you can draw them with the root at the top or with the root at the bottom. So we just had a tree with the root at the bottom, right? So when you're, well, but the most typical representation of trees is with the root at the top. And when we're saying top down, when we're saying bottom up, right, which is what you see here on the slide, when we're saying bottom up, it means that we're starting at the leaves at the lower part and we keep going up. But for this particular slide, we're going to start at the top because the top is the bottom, right? So this would be a valid tree, right? This would be a valid tree. But when you have a tree that looks like this, they should call it earth, right? No? Too early still?
Oh.
You need a cup of coffee? Right? They should differentiate. It's a very common thing, right? So very often you would see, especially in logic, you would see trees drawn with the root at the bottom. But then say it's a bottom-up approach. And then you look at the bottom and can't quite get how it works. Type safety. In a type-safe language, what's a type-safe language? A type that doesn't mix data types, right? A type where we don't allow 1 plus true, right? So now all of you know a few languages, and you definitely know languages where 1 plus true is something, right? It doesn't bump, right? You get a value out of that. JavaScript, Bash, Perl, Python. I think not, right? Python is type safe, even though it's type safe in a dynamic manner, but it's still type safe. You can't add 1 plus true, right? Oh, really? Okay. Oh, there's no real boolean, right? In Python, there's no real boolean. Yeah. So that's what's happening. That there's no real boolean. So we use the C representation of booleans, which is either 0 or greater than 0. 0 is false. Greater than 0 is, or not 0 is true. And then you don't really have you don't really have the problem of true plus 1 or 1 plus true. Okay. But you do have that in JavaScript and Perl. You are guaranteed not to have certain kinds of problems when you work with well-typed programs. You can push type safety to the point of memory safety, right? So you can prove, for instance, that you will not see crashes without an error, without a stack trace, essentially, right? So the main problems that we get from non-type safe languages are no progress and no preservation, right? No preservation means that as you move from one type to the next in your type inference, right, you lose the well-typedness of your expression, right? Your beginning and the end might be well-typed, but somewhere in the middle, you're not well-typed anymore, right? When you have preservation, this makes theories and proof very straightforward, right? Because the correctness of the end result is given by the transitivity between the steps, right? You're going from this step to this step that still has the property, and then you're going to this step that still has the property. So when you reach the end, you still have the property that you want. But when you're in this kind of languages, any kind of property that you may prove, right? You might get the property at the end, but not by a transitive fashion, right? You might in the middle lose the property and regain it later, and that may make any kind of proofs about any kind of definition of the semantics of that language very difficult. Right? So which generally, yes?
Can you give an example of expression lose the property, lose the type?
I will have to think very hard. So let me get back to you on that. I would not be able to get it right now in a few seconds. There are many. So there are languages that actually, like Scala, which is considered a type-safe language, which does not have a type preservation property. So as you infer the type of an expression, right, and you're going through the sequence of steps, at some point you're losing the well-typedness. I mean, this is something we're not going to see in this course for sure. I would have to, think a little bit, and I mean, most likely I will have to look online and find one. Okay, let's move on to defining a virtual machine for EPL. This is going to be a very simple thing, right? You're probably thinking virtual machines should be very similar to processors, and we're going back to assembly language, and but we're going to some sort of an assembly language, but nothing compared to the complexity of the Intel architecture, for instance. Simplest kind of a virtual machine is the stack machine. The stack machine has a program, right, with a program counter that moves from instruction to instruction, executes the instructions in sequence. For the time being, we're not going to use jump instructions or anything, so the program is linear, and the only memory is a stack, and we only have access to the top of the stack. All the operations will pop two values from the stack if they exist, perform the operation, and push the result back. So that at the end of the evaluation, we expect the result to be at the top of the stack, right? So if I have 1 and 2 in my stack, and I have a plus, my current instruction is a plus. So notice that the plus doesn't need any arguments because it only accesses two arguments from the stack, right? So the operation plus will pop the 2 arguments from the stack, perform the operation, and push the result, which is 3, back. Okay? So you have to think about that. All right? We have 3 types of instructions. Oh, actually, I think there's more. I don't know why I'm so. I like to put more stuff on the slide. So here I'm very wasteful. The important thing to understand is that the program is a sequence, and normally we would write the instructions one on top of the other, one under the other, right, vertically. But inside the rules, the sequence of rules is easier to write horizontally. So we're going to use the dot to signify the new line. So we're saying that, right, LDCI is an instruction with an argument, and then it can be followed by another sequence of instructions. Okay, so done is an instruction, always the last instruction, right? So it can constitute a standalone program. Any other kind of program has to finish with done, and with done. Okay, now if S is a valid program, LDCI with argument I concatenated with S is a valid program. Is that clear? LDCI means load constant integer, right? And when I do that, I goes into the top of the stack. So this is the equivalent of a push into the stack. Okay, I argument goes into the stack. We have a similar operation for booleans. LDCB B followed by S would be a valid program whenever S is a valid program, right? LDCB B is a boolean, either true or false. That B goes into the top of the stack. We have all the operations for which we have operators in the language, right? So we have plus in the language, we have a plus instruction here. We have a minus operator in the language, we have a minus instruction here, and so on and so forth. Each of these operations pulls from the stack the required number of arguments. Some of them are binary, some of them are unary. So they pull the required number of arguments from the stack and push back the result of that operation. And the type of that operation will vary according to the operation itself, right? So for instance, if we have LT, which is less than, right, the two operands will be integers, the result will be Boolean. Cool? So that's all we do. Is there any problem so far? Right? So notice that at each point, we're going to consume instructions one by one. We're going to execute instructions one by one, right? The remaining instructions in my program have to be a valid program at all times, right? And they end with done. That's why done by itself is a valid program, but nothing else without a done at the end is a valid program. All right, so now we move from dots to camel list. So now we have a list. So this LDCI1, LDCI2 plus done is a valid program. What it does is it pushes 1 on the stack, then it pushes 2, then it executes the plus, meaning that it pulls the 1 and 2, operates that into 3, pushes the result back, and it's done. And at the end of the this sequence of instructions, we have the result 3 at the top of the stack, right? That's what we will consider to be the evaluation of an expression on our virtual machine, right? We execute the instructions, and the result is at the top of the stack at the end. Cool. So we're going to define a new relation, and this relation compiles. This is a compiler, right? Compiles a expression into the corresponding sequence of instructions. All right? So this is a compiler, and it is a relation, right? Expression is in a relation with the corresponding sequence of instructions, and we're going to define it by inductive rules. Notice that we don't have a marker of the end of expression, but we have a marker of the end of the virtual machine language. So because of that, we're going to treat this done especially, right? We want to show here that done has to be at the end of the program, but since done is there, it's sort of a redundant piece of information for the compiler, right? We're only going to specify what's before the done. That's our object of our compilation, right? So let's see how we compile the constant. Obviously, you have a constant. The only thing you can do with it is push it on the stack, right? Looking at what the virtual machine can do, it's nothing much else. Of all the instructions, if you were to pick one, just without having the big picture of the compiler in mind, it's nothing much else you can do. Cool? Right. So an integer constant will be pushed via the integer pushing instruction. The Booleans will be pushed via the Boolean pushing instruction. Okay? So remember, we're looking at this S here, right? We're trying to derive this S, and there's an implicit done at the end, right? Meaning that if my program is just N, the resulting compilation would be LDCIN.done. Cool? This is just to bootstrap the math. So let's take the case of plus, right? So if E translates into S1, E1 translates into S1, and E2 translates into S2, E1 plus E2 should translate into S1 followed by S2 followed by plus. Okay? This seems like magic, right? This is really where the magic happens. So in order to understand how this works, okay, let's look at E1 first. So we have this expression E1 plus E2. Let's look at E1. E1 is a valid expression in its own right. So let's say I have the sequence of instructions for E1. Okay? If I execute that sequence of instructions, because we're putting it here, right? We're putting it at S1. If I execute that, at the end of that, the result of E1 will be on the top of the stack, right? Now, whatever I execute next if whatever I execute next doesn't consume the result of E1. So let's look at how the stack looks now, right? So I have executed E1, and my stack has only one element, which is the result of E1. Let's call it R1. Okay? So now I can look at this stack and assume that it starts here. There's nothing, you see, as far as E2 is concerned, E2 doesn't know that there was something already in the stack, right? You can just assume that the stack starts there, right? So now, let's say that E2 is the S2 is the correct translation for E2, right? If E2 was executed in isolation on the blue stack, I will have R2 at the end here, right? But because I executed on a stack that already contains R1, and because when I execute it here, it doesn't bump, means that it doesn't try to read from underneath the bottom of the stack, right? What's going to happen then? R2 will naturally be here after executing S2, right? So now we have the perfect condition to execute the plus. I have R1 and R2, both of them in the stack, and I can execute the plus and replace that with the addition of R1 and R2. So this clearly works, right? It works on the underlying assumption that whenever I execute a sub-expression, right, that sub-expression will not read from underneath the bottom of the stack, right, and will leave its result on the top. Okay, so it's a very nice isolation property, which allows me to focus on a smaller problem, right? Essentially, use divide and conquer. So this is a divide and conquer approach, right? Execute S1 first, right? Then execute S2 in the isolated environment, but S2 doesn't change the isolated environment more than it needs, right? And then because of that, there's a relation between R1 and R2 so that we can use those together. Cool? Clear? Magic. So we have a compiler for expressions on a stack machine. Yes?
S1 is to get any further complicated expressions.
Yes. Yes. Right? But the assumption is always that when I execute S2, if S2 was executed correctly, S2 would execute correctly on an empty stack, right? Because of that, right, the behavior is that at the top of the stack we have the result of R2, and throughout the execution we never try to read below. Cool? So that's why I can stack the S1 and S2 together. Yes?
How do you deal with the precedence?
The precedence is part of the abstract syntax tree, so we're sweeping it under the carpet. All right. How do you deal with precedence? So you use grammar rules with the correct associativity, and then the parser will handle it, right? So if we wanna write a parser by hand, I can show you how to write a naive parser, all right? That will handle precedence correctly. Yeah, I mean, if you're in Yak or I don't know, Antler, have you used parsers, parser generators? Yak, Antler, Bison, Happy for Haskell, OCaml Yak for. So the oldest and probably the best by many is Yak, which stands for yet another compiler, right? So OCaml has OCaml Yak. Pardon?
Menhir. Menhir.
H. Menhir.
Yeah.
Never heard of it.
For OCaml as well.
Oh, for OCaml. So it must be a new thing.
Yeah.
I see.
Based on that.
Pardon?
I think it's based
I see. All right. There are sophisticated tools. The good news is that anything you want is already written, right? So you want a parser for C. So well, let's say you want a variant of C, right? You take a parser for C, try to understand that. You tweak it a little bit, and you get it to work. Which argues in favor of me not spending time on describing that. Let's look at a few examples. So 1 plus 2 times 3 would be evaluated by the program below. We push 1, we push 2, perform the plus, we push 3, and perform the times, and we're done. 1 plus 2 times 3, we push 1, we push 2, we push 3, we push times, we push plus, we're done. Cool? All right. So we need two registers for this machine, right? The program counter and the operand stack, essentially, which needs a top of the stack, right? And what do you think? We need to execute this program, right? So we have swept under the carpet the fact that this is just a language. What you see here, okay, so we have an example here. This is just a language, right? I've already told you how to execute it, but I haven't defined it formally, right? And I should. I should define the value of a stack program, a stack machine program. Okay, so we're going to try to do that. And this is done via a transition function, and this is essentially what we call, or we're paving the way for no, this is actually small step semantics for EVML programs. So if the current instruction, SPC means the current instruction. So if the current instruction is LDCII, right, then we can say that the operand stack and the program counter pair transitions into a new stack and a new program counter, right? The program counter will always be PC plus 1 for this case, right? Remember, this is the state, essentially, this is the state of the virtual machine. The operand stack is the stack that we've seen, and the program counter points us to the current instruction. All right? And the instructions are linear, it's an array of instructions, right? So PC plus 1 means that we just move to the next instruction. So this is how we define the semantics. When the current instruction is LDCII, we're transitioning from one state to the next. The current state is some OSPC, some stack, and some value for program counter. The next instruction would be I prepended to OS, so I is pushed on the stack, and PC plus 1 is the next instruction, points to the next instruction, right? Similarly for LDCBB, right? Just that we're pushing a boolean. Okay? Whenever we have the current instruction, whenever the current instruction is a plus, right, we're going to assume that our state has a stack with at least 2 elements in it. So that is signified by having an I2, I1 at the top of the stack, right? And we're transitioning to a new state where we popped I1 and I2, we performed the operation I1 plus I2, we pushed back the result on the top of the stack, and again we moved to the next instruction, PC plus 1. Is this clear? Whenever the SPC is done, we don't quite have a rule for this case, right? Because we haven't defined, we don't have a way of saying how to access the top of the stack from the external world, right? So we're sort of leaving that, we're doing a bit of hand waving there, right? So we're saying that the result of computation is at the top of the stack whenever SPC equals done, right? So the result of the machine is a value V, right? Where if we start from an empty stack, this is how we denote the empty stack. And a program counter of 0, meaning that we're pointing to the first instruction of the program, we can transition by reflexive and transitive closure. We can transition to a stack with V at the top and some value of the program counter such that the instruction residing there is done. Is this clear? So this is what we call the result of the machine. Is this clear?
Does the star and the transition indicate, the transition can happen 0 or more times?
Yes.
Until we get.
Yes. So your first instruction could be done. Right? But the problem is that if your first instruction would be done, your stack is still empty, right? So you don't quite have a good result there. But in principle, you would a program containing just done is valid. So this is an example, right? We're starting from a state where the stack is empty and the program counter is 0. We have the program that is shown above. The first instruction pushes 10, and you see 10 in the stack, and we moved on to the next program counter, sorry, next instruction. Then the next pushes 20, so you see 20 and 10 with, when moving on to the second instruction, then we perform the plus. The result of the plus is at the top of the stack. We move to the third instruction. Then we push the 6, and we have the 6 and the 30. We move on to the fourth instruction. Then we perform the times, right? And we end up in a state where at the top of the stack we have 180, and the fifth instruction points to done. Therefore, we cannot transition any further. And by the definition of what the result of the machine is, we can state that the result is 180. Cool? So, how are we going to execute this, right? We're going to keep the registers and local variables, and we're going to have a big switch or case that essentially performs the correct operation for each symbol. So first of all, let's define the type of instructions, the OCaml type of instructions, right? Some of the instructions have arguments, such as LDCI, LDCB. Most do not. Okay, and we define all the possible operations. A program is a list of instructions, right? And it's a list, but here it's an array. Anyway, so we're gonna have a stack. We're gonna have a helper called execute. That helper is recursive, right? We're going to have to get from that set of a list of instructions the current instruction, which is C, and we check C whether it's done. We return the result at the top of the stack here, right? If it's not the instruction done, then we perform the instruction and execute from the next instruction, right? Execute recursively from the next instruction. So this proc inst will be a big switch, right? That just performs the operation exactly as indicated in the transition relation. And I think that's going to be part of the lab. Let's very quickly, let's skip the Java. I'm trying always to skip the Java, but I didn't comp very carefully, it seems, this time. I'm going to try to remove all the references to Java. So an interpreter for EPL and OCaml would look like this. We've discussed this, right? So we have the EPL interpreter written in OCaml. We use an OCaml compiler, and we get an EPL binary that can interpret EPL expressions, right? Then we have an expression called bill for some reason, and then we use that, we use this guy, right? So this guy is used here. We just produced this guy as a result of our compilation, and that executes the expression, meaning that it evaluates it. Is this clear? So we also have a EPL compiler to EVML, right? So this is a different kind of beast. It's a compiler, our own compiler, right? We have written it in OCaml, or we pretended to write in OCaml. You're going to do the full work in the lab. We're going to use our usual OCaml compiler, right? And we're going to produce an EPL to EVML compiler written in x86, which we can now run on x86 to compile an expression into VML, right? So this is what happens here. EVML, is it the same? No. So EPL, EVML, what's the point of? We also have an EVML emulator, right? So the whole point here is to create, so we're creating this building block, and we're creating the building block that we're going to put here. No, sorry. We're creating the building block that we're going to put here, right? So next slide is the building block that we're going to put here. Okay? So that's the building block. This one is the building block. We're going to have the compiler here, all right, and would execute on EVML and perform the evaluation in this way. Okay, so if we were at the Unix prompt or at a shell prompt, right, and we would have our compiler as eplc.ml, right? We could compile it with the first command to obtain, this would be the, so this would be the compiler, and this would be the emulator, right? So we have a compiler from expressions to EVML, and we have an EVML emulator. So the compiled expression executes on top of the EVML emulator. Okay? So then we compile our, this is our program, our expression. We compile it, right? And we would produce this file, build.evml. Then we execute that on the emulator, and we get a result. So it's left as an exercise for you to do that. It's going to be covered in the lab. Questions so far? All clear. Cool. Big step semantics. Big step semantics looks at input-output relationships. Okay? So instead of going through a step-by-step evaluation, we want to define an input-output relation. So we're going to start with the contraction rule again. Give me just a second. I'm not entirely sure. All right, so we're essentially discussing the distinction between big step semantics and small step semantics. So this is stuff that we've seen, right? Let me try to explain what the difference is. So when we define the dynamic semantics, we were interested in the input-output relationship, right? So we were building bigger relationships, bigger relations from smaller relations, right? In the end, saying that this big expression evaluates to this final result, right? So we were interested in hierarchically building values, right, from small expressions to larger expressions. So that is one approach to semantics. This is typically called big step. It looks at input-output relations. However, when we discussed the model for executing EVML programs, right, virtual machine programs, we defined that in a step-by-step transition, right? We're saying from program counter 0, we move to program counter 1, and then to program counter 2, right? So this is what we call typically small step semantics. It looks like it looks at a sequence of transitions that can be executed incrementally so that we reach a result. From an interpreter point of view, it is always the case that what is useful is the small step semantics. So if we write a emulator for the virtual machine, we want the small step semantics. All right? The emulator for the virtual machine is an interpreter. It doesn't further compile to x86. It uses OCaml to directly interpret the instructions and execute them as it sees them, right? So for that case, we want the small step semantics. For a compiler, however, we want the big step semantics. Think of the relationship between the expression and its program. We're creating from bits and pieces, from relations between small programs and their code, we're creating relations between the bigger expression and its code, right? So that's a big step semantics. And that is useful for compilers. Is this clear? Does it make sense? So the big step evaluation is a type of big step semantics, all right? And the transition function is a type of small step semantics. The compiler is a type of big step semantics as well. Okay, big step semantics has typically whatever is here So whatever is here and here, right, is smaller than whatever is here. Whereas in a small step semantics, what you typically have, and another thing is that what is here and what is here have different types, right? So this is an expression, and this is the value of an expression. In a small step semantics, right, what you have at the top is very small elements. There's no, let's go back to the transition function. This is one part I probably should have, right? So there's no composition here. There's nothing here that is composed into from small things into bigger things, right? At the top, or here, there's nothing, right? This thing doesn't. It's not two expressions that are going to be combined in bigger expression, and then these two things have the same type. It's a state, and have roughly the same size. So that's what we would call a small step semantics. Okay? Just remember, small step, interpretation. Big step, compiler. Cool? Questions?
What's
Yes?
the result after the big step? Is it machine code or is it?
Yes. Well, it could be machine code. It could be evaluation, right? So we had evaluation.
If you go to the slides, then you just put the that indicate is a value or
Where?
Like the last slide. Like activity step. Yeah. So V2 or V1, does it indicate it's a value or it's a, I mean like,
Yeah, so what you have, for instance, yeah, this is a value, right? So you can have a value, or you can have the code for a. It doesn't really. I mean, whatever is there is not really important, right? It's important as a matter of principle that what you have here is typically twice as large as what you have above, right? So if you look at this one, is typically twice as large as this one and this one, right? It encapsulates both. Then what you have on the left and what you have on the right, so what you have here and what you have here, don't have the same type. If you would have a P of something here, then you would have the same type, right?
so the V is machine code.
Could be machine code, could be just the value of the expression, right? So we're in the fortunate case where a big step semantics could give you the value, right? But if you're in a full-fledged program, a big step semantics cannot give you the, it can give you not the value, it can give you the function, the lambda function that provides the input-output relation for a program, right? So you have a state at the top, and whatever the state is input there, you can compute through that function the output state, which is still sort of like a compilation, right? Cool. More questions? All right. I think the labs are starting next week. I'm going to discuss with the TA. The lab materials should be out, so you can prepare a little bit if you want. Yeah, and I'll see. Maybe I'll try to be there. I have to find out the schedule first. Cool. Thanks for coming. See you next time. Yeah.
So for the lab part,
Yeah.
so we just do the it's like